Now the systems part is quite an important part. You have done signals and systems, or part of control signals and systems, and therefore you understand a little bit of continuous time systems. In this course, we're only dealing with discrete time systems. So what do I mean? All right, we go through the content. So there are lots of contents and lots of readings, but now we begin. What is a discrete time system? Simply means this, that we are going to take a sequence not of xt, but of x of n. So the input is discrete time, and the output is also discrete time. That's it. For x of n, we are observing for any values of its sequence, not only its current value, but also its past value, and theoretically we can even observe its future value. Why am I interested in future value, you might say? In a telephone, if you work for Singtel, as I'm talking, my signal is being quantized, compressed, processed, and sent across, and my friend at the other end is receiving the signal. No future values exist. That means before I talk, the signal cannot be processed. In such a system, it's called a real-time system, means that I'm only be able to use my current value and my past value to do anything I want. However, imagine that now I have recorded my lecture, and my entire 1 hour of audio signal is available to you. There's no more concept of past time and future time. You can set n to be anywhere, and on the left-hand side is the past time, and on the right-hand side is the future time. The signal, because it is a recording, exists both on the left-hand side as well as the right-hand side. Okay, so therefore, do not be surprised when I give you a system that can use future time. Okay, future time exists, of course, for a record. Now, whenever we play with a system, we want to ask the following, the following characteristics of a system, whether it is first linear or not linear. So in the tutorial, I'll give you an equation, and the first question is this a system linear or not linear? After that, we'll ask whether it's time invariant or variant, stable or not stable. All the systems that we are playing with should be linear, should be time invariant, and should be stable. But we have to check, okay? And if they are not stable, the easiest example I can give you now is if I put my microphone near the speaker, some noise will be, this speaker will be transmitting some noise. This microphone will pick it up, send back to the system, amplify it larger and larger, and then now a larger signal comes out, a larger signal goes to my microphone, and this is a positive feedback. Such a positive feedback makes the system not stable. Okay, that's the most common non-stable system that you will see. All right, then now we have causal and non-causal, memory and memoryless, so we'll come to that in the next 20 minutes. The most important, and I'm going to refresh this, is the system linear? And we are interested to ask this question. And what does linearity means here? It means that if I send x1 of n, I'll get y1 of n, for example. If I scale x1 of n by 3, for example, I will get my output by 3. Okay? So this property is called the homogeneity or the scaling property. Now, what about if I have x2 of n, and then I go through the system also? Now I get a picture called y2 of n, whatever y2 of n is. And then again, now I scale. In now example is beta, and therefore now if this system is linear, it is still beta y2 of n. So this property is called the scaling or the homogeneity property. Now, this last one more property that makes it very exciting. I have 3x1 of n plus beta x2 of n. That means now I have a signal that is composed by these two separate signals. And if the system is additive, then what will happen is, my output is, guys, the individual response. Okay, this due to this due to this. So every time when someone say, I'm going to give you a linear system, he's telling you that your system will behave in this following way. It will observe the additive property, meaning that my input, my very complicated input, can be broken into small parts. I can study this small parts response. My output is nothing but the sum of all these small parts response. Okay? Now, a linear system is very, in this example, it shows that, hey, I now have a chance to break any complicated signal into very simple parts and study individual small parts response and now add it up. If the system does not possess this property, it's called nonlinear, and we're not going to play with this. So the first question we always ask is the system linear? Check. And if we observe these two properties of additivity and homogeneity, we say the system is linear. Sometimes we use the word superposition. Superposition means these two properties exist. That's all. All right. So if we're happy with linear, then we are also interested in another property called time invariant. Time invariant means if I send the signal x of n, and if I now get a signal y of n, and if I delay my signal x of n to become x of n minus k, my output is the same output delayed by k. What does this mean? If you put a CD into a system, a CD, right? And then you play the CD or the DVD, the same output comes out. Whether you do it today or you do it tomorrow, the same output comes out. The input is delayed because I play it now and I play it 1 hour later. The same output will come out. So that's easy to understand. What about a figure? Maybe a figure is nicer. This is a linear system. Okay, this is a discrete time system. And now I'm going to send a signal, x of n. And guys, what is the simplest signal I can send into a discrete time? Impulse. Very good. Which is nothing but 0, 1 in the amplitude, and nothing else. And I have sent this signal. And the output will have some response. So this is 1 and 2. Okay? So this is y of n. Okay? Now I've sent an impulse, I get this. If I want the system to be time invariant, now I'm going to send it at 2. Okay? Time 2. I send the same impulse. Okay? And I say that the system is time invariant. What will I get, guys? I tell you, this is the input, this is the output of a linear time invariant system. I give you an impulse here. Now I give you another impulse here. The answer is the same, but delay, right? Because time invariant means the input is delayed, the output is delayed. By how much? In this example, is 2. So at 2, I will now fire 1 and 2. Can you all see? So this is a delayed version of this, y of n minus 2. Our friend here is x of n minus 2. The input is delayed by 2 samples with respect to here. The output is delayed by 2 samples. Okay? Now, if the output changes for whatever reason, then the system is not time invariant. If you have linear and you have time invariant, then later on we will achieve the convolution equation. Okay, and we'll derive that from this principle. All right, some more. Stable. I'm going to fire an impulse again. And now this is a linear time invariant system. Okay, so I've already checked. The system is linear and the system is time invariant. And I will get a response. This response has a name. Y of n is equals to, if the input is the impulse, the output is called, okay, let's try it again. The input is an impulse going through an LTI system. The output has a name. His name is impulse response. Okay, if the input is a step, output is a step response. That's all. So the word impulse response must be understood from this context. I have an input, I send an impulse through the system is LTI, the output has a special name, his name is impulse response. Finish. Now, my impulse response in my previous example looked like this, 0, 1, and all 0 after that. And this impulse response looked really simple. Okay, it's just, I send an impulse, I get 2 values out, and I get zeros. Okay? Now, I'm going to clap. When I clap, it is as if I've created an impulse. In this case, it's an analog impulse when I clap. Everything else you hear after I clap was due to the room. Nothing to do with my clap. Okay? Same as this. I send an impulse. After that, he comes out 2 values. These 2 values is due to the system. Okay? So I'm going to clap. What do you think you will hear after I clap? So let's try. Okay? So after I've clapped, about 50 milliseconds later, you can still hear some sound. Even worse now, because as I move closer to this, it goes up and come back. Okay? And if you are in Grand Canyon or in the church, you go hello, and then you go hello, 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 right? Because the sound comes backward. So now you almost understand what is called a room impulse response now. It is when I clap, what will the clap generate is the impulse response of the room. If I send an impulse to an LTI system, whatever I get is called the impulse response of the system. Something magical happened here. We usually denote the impulse response as h of n, and we are interested to find whether this guy is absolutely summable. And if the impulse response is absolutely summable, the system is stable. So if this is less than infinity, implying the system is stable. Now I can always give you another example, and now the impulse response look like this. Therefore, I send an impulse, I generate a step. So I'll ask you now, is the impulse response absolutely summable? And of course, it's not absolutely summable, and therefore now the system is not stable. Now, there are some terminology here. The word BIBO. BIBO means if my input sent to the system is bounded, is my output bounded? Okay? And the word BIBO is synonymous, almost synonymous with the word stability. What BIBO means is, if I send a very large input that is unbounded, that goes to infinity, of course the output will go to infinity in the simplest case. In this example, if I send infinity, some large value that go to infinity, then of course the output will go to infinity here. But if my input is bounded, that means among the largest value of all my x, I can find the largest value, and it is not infinity, means it's bounded. Then the question is my output bounded? So the word BIBO has this implication. Only when my input is bounded, is my output bounded? And to check for that, all I need to do is to check whether my impulse response, h of n, is absolutely summable.